Right, our recording has begun. All right, good morning, students. And we are meeting more after a week, probably. Right, we didn't have the class on Tuesday, but I hope you people have seen the assignment that has been given to you. And today at 12 o'clock is the due date that I've given. And sadly, I could see that only 42 out of 132 of you, 45. Only 45 out of 132 students have submitted the assignment. I assure whoever submitted those 45 would get 10 out of 10. The others who have viewed and didn't turn back. This is not like our class assignment. I can see who have seen the assignment and who didn't see the assignment yet. Great people who didn't even see the assignment till now. After a week also. Don't expect the full marks for sure. All right. I have changed the due date of the assignment
Ma'am,
to
hello.
yes.
Hello.
Yes,
I'm
who is
Sai Kumar,
this?
ma'am.
Yes, Sai
Sai
Kumar.
Kumar.
Yes, Sai Kumar.
Yes, ma'am. I have informed you, ma'am.
Yes, you
Hello.
did.
I didn't post, ma'am, assignment. I will post today.
Okay, that is what I'm about to tell something. I understand. I know what your problem is. I have changed the due date to submit the assignment to Sunday. All right. So by Sunday, however, how many ever assignments I'm getting back, only those students would be given the marks. All right, Sai Kumar, even you are included in that. You are not into until today, okay? Those 45,
Okay.
you can submit it. All right. Others,
Okay.
I've changed the date to September 27th, 12 p.m. Before that, I'm expecting the assignments. Both the CRs of both the sections. I insist, remind your classmates who didn't even turn back. They didn't even view what is the assignment questions either till now. You talk to them, you inform them that the due date has been changed, and they have to submit it by Sunday. All right. So today we are going to start a new unit. We are done with unit 1 and 2, and I hope you have understood what all is taught till now. If anything is there that has to be reviewed, you leave a message to me or leave a message to your CR so that we can give a class to what all topics have to be reviewed. All right. Depending upon the majority of the students only, any topic would be reviewed. If not, individually it will be clarified, because we cannot give a complete class for 2 or 3 students. All right. So 2 or 3 students can contact me separately. Anything, all the concerns, please inform it to your CRs. Right. I'll start sharing the screen now. Right. Nandita, are you able to see the screen? Moderator for today, are you able to see the screen?
Yes, ma'am.
Right. We will start with unit 3 today. All right. Is this coming like this? Right. What was unit 3? In the very first class, I have given you all the units, right? Any one of you, if you have checked this, if you are checking the syllabus, could you please tell me what is unit number 3? Or I shouldn't even expect that answer from you. Anyone who could tell me what is unit 3?
Yes, ma'am.
Yes, Shravanti.
Formulation of finite element method.
Thank you very much. So this is your unit number 3, which is formulation of finite element method. See, formulation indicates, I have already told you that whichever big structure we have, we are going to divide it into smaller elements, and then we are going to give or derive equations to them so that we can get a solution. Alright, approximate obviously, but still. Now, how is that equations, or how are we going to formulate that, is going to be our unit 3, unit 4 and unit 5 also. Alright, all the 3 units is the same, but in the beginning of the unit 3, we have these topics. If you check, uh, using principle of virtual displacement, determination of stiffness matrix of a 3-noded triangular element, that is the constant strain triangle. What is principle of virtual displacement? That was in the previous class. In under which method does principle of virtual displacement come into picture? Am I audible? I'm not able to hear you people respond.
Yes, ma'am.
Yes. For that you can give answer, but for the question what I asked, there is no response. Into which method does a principle of virtual work or principle of virtual displacement come into picture? It's just the previous class we have completed. Yes, somebody is talking. Sorry?
And Galerkin's method.
Yes, Galerkin's method. Thank you. Others, what happened to you? See, I have about 72 members are there in the class, and none of you are telling which method we have worked on, which is uh, which is giving us the principle of, which is taking the principle of virtual work into consideration. Are you able to follow FEM? Let me know that first. Are you able to understand, or your memory is going weak? All right. If you are not answering, it's going to be a one-man show, guys. This is not going this way. You have to talk, you have to interact. If not, either you will be sleeping or I would be sleeping later. No, that's not the way. All right. Using Galerkin's method, we will have to determine the stiffness matrix for a 3-noded triangular element, which is called a constant strain triangle. We can also call it a CST element. Very, very important topic, and much expected question in your external. You may mark it as important also. All right. And then we have other elements like 4-noded rectangular element for plane stress and plane strain problems, convergence criteria, discretization, assembly of global stiffness and load matrices, displacement boundary conditions. These are going to be the topics what we are going to deal in unit 3. See, all the time before we start any topic or the unit, or even after completing any topic or unit, I'm showing you back what is the syllabus. All right, this is to confirm with you that all the topics are being covered. If at all any topic is left over, it is on you to question. All right, this is not been explained. You have, if not, at the end you just cannot tell that some question have come and ma'am did not tell that. All right, you have to be responsible enough to question me back that this topic has not been completed. All right, we'll go into the formulation now. Before going into formulation, there are some basic requirements for all the 3 units. I'm not telling that it is necessary only for unit 3, but there is going to be some terminology, all right, and uh, important concepts that is needed before we start unit unit 3, 4 and 5. FEM is all new for us, all right? So what all terms we are using in FEM may not be that familiar, all right? We'll become familiar with the terminology first, and how and what are they and how they are formed, or how they are constructed, and how do we formulate them with the use of what we do formulate them. All those things we have to understand beforehand, rather than directly skipping into the formulation. All right, if at all directly skip into the formulation without telling the basics, it'll be like we are in a complete different language we people are speaking in. All right, so what we'll do, we will go with the basics required for formulation of M. All right, when I'm talking about basics, there are topics in the basics also which you may expect in your 2 marks questions. All right, now in basics we will look into element shapes. What kind of elements are there in FEM? All right, one structure is given, and you just can't divide as it is, however you want, whichever direction you want and whichever shape you want, you cannot change the elements into. All right, there are specified shapes and specified formulations that are being mentioned. All right, depending upon this you can divide the whole structure what we have. All right, now what are those elements, in what shapes are they present, and in what categories we can confine each of them into, that we can check in this. All right, and the second one are nodes. See, from the starting, we have been talking about this, FEM is like discretizing the structure into smaller elements. We don't know what are the elements. And then two-noded beam element, two-noded truss element, two-noded bar element. We have talked about this also. But what is nodes and how nodes are to be denoted, everything we are going to see now. All right. The next one is nodal unknowns. This also we should know. To which nodes, to which kind of problem uh, at nodes, depending upon the type of problem, unknowns will be changed. All right. So for what problem, what is the unknown, and how can we reach to that unknown, that we can learn in nodal unknowns. All right. And the next one is coordinate systems. See, because we are dividing the structure into smaller elements, uh, we have different type of coordinate systems arranged. Uh, if suppose if at all you are taking the element from a huge structure and trying to derive it first, the coordinate system with respect to that element we are calling that as local coordinate system, whereas the whole structure, when you combine all the elements together, that we are calling it as global coordinate system. Like that we have different coordinate systems also available. All right, and the final one is shape functions. Very, very important. When I was first introduced to FEM, it was clearly shown that FEM is all about shape functions. All the formulation, all the analysis, everything for every node depends on shape functions only. Now, what are these shape functions, to which element, how do we derive that? We are going to see in the further classes. But what are shape functions and why is that so important? We will look into that in today, or hopefully in the coming class. All right. So these are the basics that we are going to learn today. So we will start with elemental shapes first. All right. If there is any difficulty in the audio or the video, you may please raise your hand so that I can understand. All right. It's very calm. I don't know whether you just left your screens or you're listening. That is up to you. All right. We'll start with elemental shapes. Based on shapes, elements are classified into various types again. All right. Is somebody speaking? Bilal? Bilal. Bilal Siddiqui. Roll number 1.
छोटे बच्चे को क्या पालना।
Bilal.
Ma'am, I muted Bilal, ma'am.
It means he's not listening the class. He just left it over there and he's talking. Very bad. Please take care of this, Nandita. It's
Okay, ma'am.
thank you. Thank you very much. All right. Now, based on shapes, elements are classified into various types. All right. Under this, if we check, we have one-dimensional elements, and then we have two-dimensional elements. We have axisymmetric elements, and then finally we have three-dimensional elements. All right. Give me a yes once you have noted it down. Anyone?
Yes, ma'am.
Thank you. Now we will try to see every type of element individually, because every type of elements has its own way of taking into consideration what for different problems different type of elements are taken into account. All right. So we will see individual elements first. So first one is one dimensional elements. All right. The name itself insists that it is one dimensional. When we spoke about this in the first unit, what is told, can anybody mention what are one dimensional problems? In what way the load is applied, or while we are deriving the stiffness
Your voice
matrix
is
we have
not
seen.
clear, ma'am.
My voice is not clear. Wait. Is it clear now?
Yes, ma'am.
All right. Anyone, when we have seen in the first unit, what kind of a load is expected in a one-dimensional element? Can anybody answer? What kind of force is expected in one-dimensional problems?
Linear.
Some of the word is yes.
Axially.
Exactly. Axially or linearly, right? Okay, but axially would be more preferable. Thank you. Axial loads or axial forces are being expected in one-dimensional problems. All right. So when one-dimensional elements are taken into account, it means that the force is expected to be going axially. So we are, whatever we are going to derive depends upon the axial force. All right. So one-dimensional elements are suitable for one-dimensional problems only, and may also be called as line elements. We have seen this already, you know, your line elements, bar elements, or all these things come into one-dimensional elements. All right. So how are these going taken into picture? You can look here. One-dimensional element doesn't mean it will have only one node. All right. If at all one node is there, you're not going to reach to any solution, by the way. All right. So there are two nodes that are being given to one-dimensional element where on the load is applied or load is expected in axial condition. All right. So does it mean that one-dimensional element will have only two nodes on the corners? No, that is not possible. All right. There is a possibility that there would be number of nodes. There would be more number of nodes. All right. Higher order elements are also possible in one-dimensional elements. All right. Look here. This is three-noded line element, and this is four-noded line element. All right. There can be any number of nodes be present depending upon the type of problem. All right. How what kind of solution we are expecting. All right. It is like, you know, number of nodes, you know, your interpolation function, what you are trying to do is that big. and the solution what you get is also expected to be uh, you know uh, approximated to that level. All right, more profound answer. All right, so these are the higher order line elements. These are four nodes. It can be any number of nodes. If at all n number of nodes mentioned, it is going to be in this way. All right, you may please note down all the pictures and give me a yes. You got to be a little bit fast because there are many figures that we are going to look into. If we take so long, basics cannot be completed in one class.
Done, ma'am.
Right. I'm going for this is all about the one-dimensional element. When in further classes, when we are trying to formulate, when I mention one line element, it does mean it is one-dimensional element. All right. All the time we don't have to mention one-dimensional line element. When it is line element, it directly means it is one-dimensional element. Please remember and underline and keep line element. All right. So that when you are reviewing it, that will be easy for you. Right, next one is two-dimensional elements. All right, so we have seen already when one-dimensional elements are suitable for one-dimensional problems, it does mean two-dimensional elements are suitable for two-dimensional problems. Now can anybody mention or name any two-dimensional type of problems? In the starting classes itself, it was told to you, nothing new. We're just trying to uh, see what kind of elements are there. Two-dimensional problems, anyone?
Beam is considered as two-dimensional.
Right. Okay. Beam can be considered as three-dimensional also.
Paper, ma'am.
Sorry?
Example paper.
Paper is an example. Good. In what what type of problem can you keep that example into? It's a 2D. It's a 2D problem, definitely. In 2D only, I have given you two types of um, problems in the
Plate,
previous
ma'am.
classes.
Plate.
Yeah, plate, good. Okay. A plate also not completely into 2D, depending upon what is the requirement of the analysis that you can take. Nobody remembers plane stress and plane strain. It's completely 2D. Only X and Y is present. We're taking so long to think about it. Stress analysis in plane stress, plane strain, and plate problems are the two common 2D problems you can find. All right. You may please underline plane stress, plane strain, and plate problems. In plate also, the sometimes where bending has to be taken, we may go into a higher order. All right. Now, for this type of problems, what kind of element is used more, or what kind of element is considered to get into the solution is a three-noded triangular element. All right, a three-noded triangular element. This is the element that is called as a basic and the first and most used element. When a structure was to be defined or analyzed in using FEM, the first type of element that it was taken into account was a triangular element. All right, smaller in structure, 2D type of a model, and uh, it is like you will have three nodes which can be connected to the other elements that are there along the whole structure. All right, so this is one type of basic element that was uh, taken into account. All right, that was to be precise, it was the first element that have started where analysis was doing being done in FEM. All right, now this three noded triangular element, please remember, only three noded triangular element is called constant strain triangle, CST element, constant strain triangle, or a linear displacement triangles. Any of the names is given to the three noded triangular element only. All right, constant strain or linear displacement. See, we have a triangular element. It need not be a equilateral triangle only. Any triangular element, all right, which have three nodes. This is called a CST element. You may please take down the picture also. So whatever the derivations or formulations we do with respect to nodes for a 2D element, we precisely consider a CST element only. That is what is there in your unit 3 also. All right, determination of stiffness matrix for a CST element. Now, is it like the triangular element is only confined to three nodes? No, that is also not right. There can be higher order um, triangular elements also. All right, but the thing is, it is not called as CST element. Who is that? Can I go to the next slide, please? Are you done with the figure? Are you done with the figure?
Yes, ma'am.
Oh my God. Nandita, who was that?
Ma'am, that's Mohammed, roll number 27, ma'am, 16 series. 160715.
I thought it was roll number 30.
30.
Mohammed Gauss Sharif.
15 series.
Yes.
Sir, good morning, sir.
Good morning, man. Just remove him from that class. Give him absent.
Yes, sir. I removed him. Nandita, please look into it that, okay?
Okay, ma'am.
All right. I'm going to the next slide.
Ma'am, we can't see your slide.
Hello?
Just hold on. Huh? Madam's connection might have dropped, so she will be joining. Just hold
Okay,
on.
sir.
Alright, sorry about that. I just got disconnected. I'm resharing it. Right. Are we done with this figure? I need a yes, please.
No, ma'am.
Do it fast. It's just a triangular element with nodes. All right. If at all we have to go for the next higher order triangular element, what would be the name of that? We have seen two already. If I have to go to the next one, can you guess or can you expect what would be the name of the next triangular element? Any one of you? Guys, please talk. When the question is asked, you are expected to answer.
Ma'am, binary, maybe
Who is this?
Javeria, 41.
Okay, Javeria. No, look into the two elements that are already given to you. When it was a three-noded triangular element, its name was constant strain triangle and or a linear displacement triangle. All right. That is when it considered for six-noded triangular element, it was named linear strain triangle. Strain triangle and displacement triangle did not change. It is that just that in the place of constant, linear has come for the higher order. Like that, if we take for the next higher order, for strain triangle, what term would be taken into account? It's on the screen. You can look into that and tell.
Quadratic strain triangle.
Thank you. That's good. That's good. That's exactly right. When we are going for the next higher order, if at all, this is the see a triangular element if I consider, this would be the next higher order that can be taken into account, which is of 10 nodes. All right, which is of 10 nodes. It looks like a grid points. All right, in previous one for each side there was one node given. Now here each side is given two nodes. All right, so this is called 10 noded triangular element. This is called quadratic strain triangle. All right, which was the name in the previous one? If you see, it was quadratic displacement triangle. When it is into higher order, the quadratic is taken into strain place, that is quadratic strain triangle, or it can be called as cubic displacement triangle also. All right, cubic displacement triangle. It is 10 noded triangular element. So next higher order would be, other than Shravanti. Shravanti already answered.
Cubic strain triangle.
Thank you. That's good. You're done with the figure. I'm going for the next one. Are you done with the figure?
Yes, ma'am.
Right. If at all this is the triangular element, we are going for higher order rather than the previous case. How many nodes are you expecting for the next higher order? For every surface, there were two in between in the previous one. So it would be 3 now. All right. In such a case, we're going to get 15 nodes. So a 15 noded triangular element is called as a cubic strain triangle or quadric displacement triangle. All right. So this keeps continuing whenever you have to go for higher order, it goes on this way. So the next would be with 4. So it will be 21 noded. So 21 noded, uh, I have named it as 10 only. '21 noded triangular element, it is called quartic strain triangle. All right. These are some different types of one element only. We have seen it as a triangular element only, but of uh, n number of nodes are being added to it. All right. So it is not like when we have a triangular element, it doesn't mean we have nodes only to the corners. All right. If at all triangular element, only to the corners, if we see, that is a basic CST element. All right. Now, why these nodes, when they are taken into account, why we are taking in between, or why we are taking inside the element? When we are learning about nodes and nodal unknowns, you can understand that. All right. But this is the way. Please, whatever the numbering that is given to the nodes, you may look into that. That has to be given exactly the same. Why they have to be given like that? I'll tell you in the next coming slides. All right. Please do not interchange the numbers that are being given to it. Give me a yes once you are done with the figure. It is not like you can just write down 21 notes and give the numbers however you want. That you cannot do. Please give me a yes, please, once you're done. And please do not take so long. I'm going forward. You may check this in the video sessions after the class. All right. Or you have your textbook PDF that is given to you. You can check the figures in that also. All right. Now the basic 2D element we have seen is a 3-noded triangular element. All right. But when it comes to 2D, it is not like we have only triangular elements that are possible. All right. There is an other type of element that also exists, which comes under 2-dimensional element category only. All right. That is 4-noded rectangular element. A 4-noded rectangular element is also a 2D element, but it is like it is used very less. All right. When 2D element is 4-noded rectangular element is taken into picture, it is constructed in such a way that its sides are parallel to global coordinate system. All right. Now it is very easy to construct. Okay. Rectangular elements are very easy to construct in the structure, but when there are inclined boundaries, this one will not give us the proper solutions. That is why we prefer a triangular element as the basic one, because inclined boundaries conditions also can be solved easily. All right. Now if we think this is the global coordinate system, then this is the rectangular element with 4 nodes. So this is a 4-noded rectangular element. For this also we have to derive the stiffness matrix. Please remember that is there in your unit 3. We have seen in the syllabus in the beginning. All right. I need a yes once you're done with this figure, please. Excuse me. Do not take so long. Please do it fast. We have much to complete.
Done, ma'am.
Thank you. Now we have seen when it is about the CST element, the nodes are not just confined to the boundaries only, or the edges or the corners, anything you can name it. When the triangular element is there, in rectangular elements also there can be higher order rectangular elements. When I indicate higher order, does mean that a number of nodes are more. All right, I'm trying to tell that. All right, so when this or the rectangular elements of higher order can also be used, but there are two methods when it comes to rectangular elements, or two types of node considerations that can be taken into account for rectangular elements. All right, one is nodes are in the form of grid points. All right, grid points indicates it looks like a mesh if we join them all. All right, such type of rectangular elements are called Lagrange's rectangular elements, or simply Lagrange's rectangles. When nodes are only along external boundaries, there are no internal nodes. There are only nodes to the edges or the surface of the rectangular element. That kind of elements are called serendipity rectangular elements. All right, this terminology is very important. Please underline them and keep Lagrange's rectangles and serendipity rectangles, because when we go forward, when problems have to be solved, uh, what kind of rectangular element it is has its own type of solution. All right, Lagrange's have given a different type of approach to get the solution for that. All right, we will look into that. So now, if this is the rectangular element, this can be one type of node consideration that can be taken into account, which looks like a grid, more higher, even more higher order. All right, this kind of rectangular elements where if you clearly see the nodes are in a form of grid points. All right, these are called Lagrange's rectangles. All right, I did not give the numbers to it, but you can do that, but don't do it now. Don't give the numbers now. When you learn about nodes, you can understand which node has to be given which number. All right, that is also mentioned. All right, these are Lagrange's rectangles. Can I go to the next slide, or you want me to wait?
Right.
Okay. Give me a yes, please, once it is
Yes,
done.
ma'am. Complete.
Okay.
Yes, ma'am.
Now,
Yes, ma'am.
nodes are only, okay, thank you. Thank you very much. When nodes are only along the external boundaries, we are calling that as serendipity. These figures, what we have seen, belongs to Lagrange's type of elements. Now, this is the basic four-noded rectangular element what we have seen. All right. This comes under serendipity type of rectangle. Now, see, this is another model when we are going for the higher order, and this can be the next one. All right, so these type of ones are called serendipity rectangular elements. All right, where if you clearly see, the nodes are given only along the sides or the surface of the element. These are called serendipity type of rectangular elements. You may please note down the picture. Can I go to the next slide?
Yes, ma'am.
All right. Now we have seen in 2D elements, two-dimensional elements, there was for the inclined boundaries also we have seen triangular as the basic one, and for the four-noded we have seen rectangular as a basic one. All right. Now with the four-noded only, if at all inclined also has to be taken into account, there is an other type of element that is also available. All right, but it is not much used. That one is called quadrilateral elements. All right, this also comes into 2D elements only. All right, quadrilateral elements. These are the 2D elements developed by combining triangular elements. It has not been used much after the development of isoparametric concept. Now, what is isoparametric concept? We are going to see in the next chapters, but giving you a brief where curved, see, structures are not always with the, straight edges. You cannot find always a triangle or always a rectangle kind of a thing, or corners or the edges are just not as straight as possible. There are possibilities that you can have a structure that has to be analyzed with curved boundaries. All right, for the analysis of such type, isoparametric concept was taken into account. All right, so the curved boundaries are also uh, are to be analyzed. It's not like we are going to analyze only the straight edged ones. All right, see, if at all this is the global coordinate system. See, this is a quadrilateral element, four noded, but there are inclined also. Now here I have mentioned that it is developed by using by combining triangular elements. If you clearly see, two triangular elements combined together is making a quadrilateral element. That is what I meant. Two triangular elements with or you can just tell it as two CST elements combined together is forming a quadrilateral element. That is what I meant. All right, are we done with this figure?
Yes, madam.
Thank you. See, a combination of two triangles will form a quadrilateral element. Combination of four triangles also can give a quadrilateral element, but the number of nodes would be 5. That is the next higher order. See, combination of four elements, but with 6 nodes each. So this also can be called as a quadrilateral element only, but of a higher order. You may note these pictures also. So as simple, if we think quadrilateral elements are the elements that are developed by combining triangular elements. It may be any number, but at the end what we are getting is a quadrilateral element. All right. Are you people following?
Yes, ma'am.
All right.
Yes,
Yes,
ma'am.
ma'am.
That S itself is telling me how sleepy you guys are.
No, ma'am.
All right. What we'll do, we'll have a quick poll. All right. So that I can understand that you people are attentive.
Thank you, madam.
Just a second. Where is the option for poll? It's missing. Not finding the poll option here. I think there has been some changes or something in my system. All right. Okay. All right. I'm unable to give poll. We'll see that in the next class. We'll continue with session today. Right. We're done with these figures. Are we
Yes, ma'am.
done with these figures?
Yes, ma'am.
Okay. We'll go
Yes,
forward.
ma'am.
Thank you. Now, we have seen a topic that there is a concept of isoparametry which was developed, which was helping for the uh, analysis of curved boundaries also. All right. In such a case, uh, using isoparametric concept, even curved 2D elements are being developed. All right. To take care of boundaries with curved shapes. They look like this. Triangular element only, but curved boundaries. All right. You may please note down. These are all isoparametric 2D elements. When in the structure there are curved boundaries, then this is taken into account. How this for this we can get the solution, we'll see in the next classes. However, this topic is there for us. Give me a yes, please, once you're done.
Yes, madam.
All right. So this is all
No, ma'am.
about
No,
the
ma'am.
two. Okay. This was all about the 2D elements. We have seen four different types of 2D, two-dimensional elements. That is the basic one was triangular element. Then we have four-noded rectangular element. Basic is a three-noded triangular element. Please, unless you have to speak, then only unmute yourself. the whole class. All right. When we then the next one we saw was a quadrilateral element, which is the which is developed by combining triangular elements, and then finally the isoparametric 2D elements also we have seen. All right. What is the next type of elements are there? What is the next one? One dimensional is over, two dimensional is over. What is the next one?
Axis.
Axisymmetric
Elements.
All right. Ever heard what is axisymmetric elements?
No, ma'am.
See, you are in the final year. You must have definitely heard what is axisymmetric.
I heard about symmetric.
That's a good answer. All right. When it is about axisymmetric, it means it is formed by with the help of one-dimensional element or a two-dimensional elements. Let me tell you an example. Right. Are you able to see? Are you able to see me clearly? See, I have a paper with me. Can you see?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Yes.
Now see, if at all this paper, which is of a rectangular shape, with uh, any of the side,
Ma'am,
if I take, sorry,
the
Madam,
paper
blur
is
ga na
not
audutundi, madam.
clearly seen. The background is covering the paper, ma'am.
wow, that's great. All right, we'll do a craft work for yourself then. How is a cylinder formed? Cylinder. You know what is a cylinder?
Yes, ma'am.
How is a cylinder formed?
With a rectangle, like when you fold it.
Not folded.
Yeah, like a development.
When we
When you
roll it.
revolve along with the surface with one side, you can form a cylinder. Similarly, a cone is formed using a triangular element. If you take an isosceles triangle or something, not isosceles, right angle triangle. When you take a right angle triangle and with respect to its vertical axis, if you revolve it, all right, then you can see a cone formed, right? These type of structures are called, I'll start sharing again. These type of structures are axisymmetric elements, but not exactly cone or cylinder. Ever heard what is a frustum? Frustum.
No, ma'am.
When a cone is cut at any height, all right, where the base and the top are both circular in structure. When you look at a cone is you have an apex and at the base you have a circular cross section. But frustum is when you cut that cone, when you do a vertical, when you take a vertical cross section over that, you will have a not apex but a circular surface. I'll show you the picture, you can understand that these type of or a ring element, you have a triangular element, you revolve it around with respect of some axis taken into account. All these type of elements are called axisymmetric. I'll show you the pictures. See, these are known as ring type of elements. All right, ring type of elements. These elements are useful for the analysis of axisymmetric problems. All right, what are these axisymmetric problems are? If you have to analyze cylindrical storage tanks, then you take this type of element into picture. All right, when we have to analyze shafts or rocket nozzles, all these are not your regular triangular or rectangular elements. All right, for such type of problems you have to take axisymmetric elements into account. All right. Now see, these elements can be constructed from 1D element or 2. That is what I mentioned. When 1D element, if we have a line element, well, the line element with certain axis or rotated, you will form a different. You will have a formation of another structure or the other element. Those are called axisymmetric. All right. When 1D axisymmetric element is a conical frustum, and 2D axisymmetrical element is a ring element with triangular or quadrilateral cross section. If three noded 2D element is taken into picture, then it is the ring element with triangular cross section, 3 noded one. If quadrilateral cross section, it means 4 noded one. See, these are the pictures. This is a conical frustum. We have a cone. Mute yourself, please.
Ma'am, that's a sir.
Who is that? You may mute them. That's okay. You have the option to mute it.
Okay.
You can mute. If you see, this is a conical structure. When the conical structure is cut at any height, all right, the leftover part that is formed, this is called a frustum. All right. So a line element, when rotated about its axis, it forms a cone. All right. Now that cone, when it is cut at a height, it forms a frustum. This is called a conical frustum. This is this axisymmetric element formed out of one-dimensional element. And if at all it has to be formed out of the two-dimensional element, see, this is the, what type of element is this? What type of element is this? I need the answer, guys. I'm showing you, the pointer is showing you what kind of element it is.
The T-noded triangular element.
3-noded triangular element. I have given you in the previous one, you see 2-noded axisymmetric element, 2-dimensional. Ring element with triangular cross section or quadrilateral cross section. If you see, this is a ring element with triangular cross section. So the axisymmetric element formed or developed using two-dimensional element, that gives a ring element. Ring element with triangular cross section. There is always a possibility that a ring element can have a quadrilateral cross section also. Cross section, you understand, when you cut at any section, any part of the section, how the cross section looks. All right. If at all it is a triangular cross section, it looks like this. If at all a quadrilateral cross section, that depends on type of the problem when we look. All right. Basically, when we take a ring element, this is how we take into account. So these are the type of axisymmetric elements that we have to solve the problems. All right. What are the last type of elemental elements we have based on shapes? Excuse me. What is the last type?
3D dimensional.
Exactly. Not 3D dimensional. 3-dimensional.
3-dimensional.
3-dimensional elements. Good. The final one, what we have is 3-dimensional elements. We have seen what is 1-dimensional. We have seen what is 2-dimensional. We have also seen what is axisymmetric. All right. The last one we have is a 3-dimensional elements. All right. The basic element for 2-dimensional was a 3-noded triangular element. All right, which have nodes taken at every corner. In the similar way, for the 3-dimensional element, the basic element is a tetrahedron element, which have 4 nodes, that is for 4 corners. All right. See, this is a tetrahedron element. Why is this called a basic one? Is it can solve the inclined structures also. All right, when there are inclined boundary conditions, then this will help to solve the inclined boundary conditions also. All right, the basic element for a 3D problem is a tetrahedron element with 4 nodes at each corner. You may please take the picture. 4 nodes at each corner. Yes, who is that?
Example for departmental store.
Ma'am, that's Prashant.
Prashant? Prashant.
I muted, ma'am.
Yeah, but these people they're not even unconscious. Guys, please mute yourselves unless you have to ask a doubt. You better raise your hand if at all you have to speak. The moderator will inform me, then we can have the discussion. You're just unmuting in between, that is disturbing the class. All right, are we done with this figure?
Yes, ma'am.
All right. See, as of in the
Yes,
2D
ma'am.
element, thank you.
Yes, madam.
As of in the 2D element, a triangular element also was the basic one. But it doesn't mean they didn't have other type of elements. There was rectangular element also, there was quadrilateral element also, there are isoparametric elements also. In such a way, this is the basic one, but there are other type of 3D elements also. All right. See, 8 noded 3D elements are hexahedron or a regular prism. See, rectangular prism is also a particular case of hexahedron only. See, this is a hexahedron, arbitrary hexahedron, which is of 8 nodes. All right. If at all rectangular prism or the brick element has to be taken into account, the whatever the hexahedron we have, there are no inclined, there are just 90 degrees. In such a way, we are calling it as a rectangular prism, which is a particular type of hexahedron only. Both the things are higher order 3D elements only. All right, they are 8 noded 3D elements. Just as we see in the 2D only, we are seeing in 3D. All right, in 2D it was 3 noded triangular element, which was basic. In the 3D it is 4 noded tetrahedron. When we are going for the higher order, it is 8 noded for 3D element. All right. I hope you're done with the picture, or you want me to wait? Are we still in the class?
Madam.
Are we done? Are we done with the picture? Can I go to the next slide?
No, madam.
Please
No,
do it
madam.
fast. All right, please do it fast. So what was the element that was available in 2D element, which will help in the analysis of curved boundaries? Any one of you? We have just seen in the 2D element. What are the elements that that helps in the analysis of curved boundaries? I'm asking you a question from today's class only.
Isoparametric concept.
Yeah, isoparametric elements. Thank you, Chandana. In the same way, for the 3D also, when isoparametric concept has to be taken into account, all right, it would be in this way. 3-dimensional quadratic element. This comes into isoparametric element of a 3D type. You may please take this picture also. three-dimensional quadratic element. All right, this element helps to reach to the solution with for the structure with curved boundaries. So by this we are done with the first topic, that is the elemental shapes. All right, the basics what we have to know, all these are done by this picture. That is, we have seen there are based on the shape of the element, there are four categories of elements that are available: one dimensional, two dimensional, axisymmetric and three dimensional. All right, we have seen all types of available elements that are there. All right, what is the next topic that we are going into is, I'm changing the slide. I hope you're done with the picture. I need a yes, at least the moderator.
Yes, ma'am.
All right, thank you. Now we will look into the next topic, that is nodes. Now see, nodes are not new, but if at all somebody asks you to
Ma'am, your video is hanged.
Hello.
I'm very sorry. There is again a technical problem. All right. Are you able to see the screen?
Yes, ma'am.
Awesome. Thank you.
Yes, ma'am.
Sorry about that. All right. We will look into nodes. Can you define nodes, anyone? Any one of you? What you understood by node, you can tell that. No? Nothing you understood? Any answer would be okay. What is a node you understood till now? That also you can answer, please. Any one of you? There are about 70 people. Any one answer would be okay.
Points.
Sorry?
Selected points.
Selected point. Okay, who was that?
Shrikant.
Okay, Shrikant, fine.
It is a
Selected point, fine. The next one, somebody is telling.
the point common to two or more elements.
Very good point. So it is a selected point and it is common to two or three elements. All right, fine. Any more answers?
It is a point of intersection of the line.
Point of intersection. Actually, no. You don't intersect any of the elements here. We just give them nodes so that it would be connected with the adjacent elements. That's all. So that answer cannot be taken. Sorry. Any more?
Unknown finite elements.
It represents.
Unknown? Who was that?
Unknown finite elements.
Unknown finite elements. Who was
A
that, by
point
the
in a
way?
network.
Who was that who told unknown finite elements?
329, ma'am.
You can tell your name.
Anil Kalal.
Okay, Anil. Yeah, Nandita, you were telling something?
It represents the possible movement in the beam or in any structure.
You mean to tell degree of freedom?
Yes.
Okay. All right. Not exactly, but that can also be taken depending upon the type of problem. Yeah. Somebody else was telling. Funny, are you telling something?
Madam, it is a connection.
Okay, Vinod. Okay. Connection, it was already told. An answer was already given. All right. All your
A point in
answers.
a network.
Sorry? I got somebody told the answer. Yes, please.
A
Go ahead.
point in a network.
The point in a network. Okay, good. Good answer. All right. You are telling it is a point. Very good. It is interconnected. Very good. Where you have to find out the unknown finite elements, also somebody told. Very good. Where you have to find a degree of freedom, you told. Very good. All these things can be combined into the answer that for any element, somebody told as intersection, but you can call that as internal nodes. Okay. Uh, that also can be taken into account. But the thing is, the node points are the selected points, good, where unknowns has to be found out in the finite elements. We can change it this way: finite selected points where unknowns has to be found, which are interconnected between the elements in a structure where the displacement or movement or anything has to be found out. This can be a total definition for the nodes. All right. I have taken it all from your answers only. All right. All are correct. Anything you can be taken as a correct answer itself. All right. So if we define it in that way, nodes are the selected finite points at which basic unknowns are to be determined. That would be the answer. What all you said is also right. They are interconnected between the elements. There is a possibility of intersection, not intersection, but interconnections between the nodes, maybe at the corners or the surfaces. All right. So why these nodes are selected is at that nodes you're going to find out your basic unknown. For the elastic problems, displacements are the basic unknown. If you find out the displacements, from displacements you can find out the slopes, deflections, stresses, strains, moments, everything can be found out when you have one term, which is displacement. So basic unknown. So at the nodal points for our topics, what we're going to see further, our basic unknown is displacement, for to which we are going to derive from the nodes. All right. Now these nodes, what kind of nodes we can take, where we can take, how we have to number them, that are specified. Okay, that is why in the previous case when we are seeing for the triangular element, I told you what numbers is given to you in the picture, please write it down as it is, because you cannot change the format how it can be taken. That is how when you give it into a software or anything, that is the way it takes. All right. Nodes are divided into two categories. All right. One are external nodes, the other one is internal nodes. All right. External nodes are taken as either when they are at the edges or when they are at the surfaces. All right. When they are at the edges also, they are called external nodes only. When they are on the surface also, they are called external nodes only. Both the cases, they are external nodes. And the other category what we have is internal nodes. All right. In external nodes, there are again divided into two categories. They are primary nodes and they are secondary nodes. Simple. When they are at the corners, they are primary nodes. When they are at the on the surface other than the corner, they are called as secondary nodes. All right. When they are internal node, it means it is inside the element. All right. We have seen all the elements till now in the previous case: triangular element, rectangular element, quadrilateral, higher order, Lagrange's, serendipity. All these things, in those elements, there are three types of nodes happening: primary nodes, secondary nodes, internal nodes. All right. See, we will look into this. External nodes. Primary nodes occurs only at the corners. All right. And the secondary nodes occurs along the sides of the element but not at the corners. Please underline a not at the corners. When this is where you get confused. Secondary nodes will not happen at the corner. I'll show you the example. See, this is the line element. All right, one dimensional. I have 4 nodes for this higher order. I'm not just taking 2. Okay. Now the 1 and 2 are given at the ends. That is what, if you remember the picture you have seen, if you can turn back your pages to one dimensional element also. All right. Primary nodes, that is the nodes at the corner, are always numbered first. If you can see the higher order rectangular element, higher order triangular element also. The numbers that are given to them, the corners are given numbers first, boundaries. Then we will have secondary nodes. 3 and 4 are secondary nodes. All right, which are on the surface. Because it is a one-dimensional element, there is no possibility of having an internal node. All right, internal node indicates it is inside the element. Line element, there is no talk about internal content. All right. So if that example has to be taken, see, we will take the linear strain triangle. Linear strain triangle means a 6-noded triangular element. All right. In this, if you see, anyone, what are the primary nodes? You may unmute and speak.
1, 2, 3.
Exactly.
1,
1, 2, 3 are primary. And the rest over which are on the surfaces, that is 4, 5, 6 are secondary nodes. Got the point? You understood? So that is why always we number the corner points as the primary nodes first. And there is a special, you may make a note of it. The primary nodes or the secondary nodes or overall the external nodes can be interconnected with the adjacent elements. All right. But when it comes to internal nodes are specific. They are specific only to that element. Suppose I have a quadratic, I'm taking a quadratic strain triangle which is of 10 nodes. See, from 1 to 9, any of the node can be connected to the adjacent available elements. But when it is about node 10 cannot be connected to any of the nodes, any of the other elements that is available. All right. So that is called an internal node, which is inside the element. It is specific for this element only. It will not be represented to any other element that is adjacent to it. All right. Now, why this internal node is taken into picture is when we have to form the interpolation functions, we consider the geometric isotropy. For that, we consider internal nodes into picture when it is about the higher order elements. You can understand the terms, what is isometric, geometric isotropy, or what is interpolation functions. You might know it earlier, but when we are trying to form the equations, you can understand what I'm talking about. Please underline the geometric isotropy and specific. All right. Now, here 1, 2, 3 are primary nodes. Can anybody tell me what are the secondary nodes?
4, 5, 6, 7, 8, 9.
And the internal is 10.
10.
Thank you. Who was that?
Shrikant, I am.
Sorry. All right. All right. See, I have taken what kind of rectangular element is this? Can anybody answer? What kind of rectangular element is this? What kind of rectangular element is this?
Serendipity.
Serendipity.
Look clearly. Lagrange's.
Lagrange's.
Serendipity means the nodes are only to the boundaries of the surface only. External. There would be no internal. Alright, don't get confused. It is Lagrange's type of rectangle. So it is 9 noded. So from this 1, 2, 3, 4 are termed as primary. 4, 5, 6, 7, 5, 6, 7, 8 are secondary nodes, whereas 9 is the internal node. So understood in the previous case what all we have seen. Why did we take only all the numbers outside and the boundaries? Why did we specify the numbers like that? If you have written numbers however you liked, then that is wrong. Go in an order. See this triangular element here. Primary I have given 1, 2, 3 to the boundaries. Next immediately comes the secondary 4, 5, and that has to go in an order. See, this is the order I have taken. All right, it has to go in an order. Same with this one also. 5, 6, 7, 8. That is because I have taken 1, 2, 3, 4 in anti-clockwise direction. All right. See, in the serendipity and the Lagrange's, what we have taken, we did not denote the numbers to those elements. If you remember, when we are looking into rectangular elements, now it is your turn that you number those nodes in the Lagrange's elements and the serendipity elements. All right. So by that you can understand how much you got the concept about nodes. All right. The only thing what you have to remember is only external nodes can be connected to the adjacent elements, whereas internal nodes are specific. So whatever solution you get for this nodes, all right, the displacement whatever we find out is confined only to this element only. All right, that answer cannot be, whatever the displacement value you have got for that particular node is not related to any of the other elements that are available. That is only to this element. That is why internal nodes are also taken into account. All right. So we are done with nodes also. What is the next topic we have? We have 5 more minutes. I hope we can finish. What is the next topic we have?
Nodal unknown.
Nodal unknowns.
Yeah, we will see nodal unknowns also today, so that in the next class we can see what are the coordinate systems and shape functions. All right, hope you're following, or should we stop it here? Yeah, 5 minutes. Why to waste that? Yes.
Can you show the axisymmetric element?
Axisymmetric. Okay, just a second. Yeah, what is wrong with this? Is this the slide that you want?
Matter, ma'am. 15th slide.
What happened in this? You have a doubt or you didn't note it down?
Note it down, ma'am.
Okay. So we are losing time. Please, can you do it faster? We are going to see nodal unknowns also. Or we'll see nodal unknowns, coordinate systems, and shape functions in the next coming class only. Are you done? Whoever asked for this axisymmetric, are you done? I hope it was funny.
Yes, ma'am.
Is it done? I hope
Done,
that's a
ma'am.
yes for that only. All right.
Ma'am,
Yes.
hello. Ma'am, I have logged in and logged out 3-4 times. Will I get attendance or not?
Who was that?
329, ma'am. Anil Kalal.
I'll check your complete how much time you were present in the class. Depending upon that, we'll look for the attendance. Do not worry.
Okay, ma'am.
Okay. Number 43. I can't hear you. I can't hear you, ma'am.
Yes, ma'am. Present, ma'am. Hello.
See, when I'm in the presentation, I cannot come back to answer you. You should unmute yourself and speak, then only I can. Okay. All
Okay,
right. For
ma'am.
today, I'm taking the attendance. See, under screen sharing only, I'm taking the attendance. Okay. So you can see that your attendance have been noted.
Okay, madam.
All right. I stopped sharing the screen. And thank you, Nandita, for moderating today. I'll stop the recording now.